So great to see all of you on this chilly evening. So I'd like to tell you about unsolved mysteries of fundamental physics. There's been a lot of talk lately about problems facing physics, where it will go next, and so on. So I'd like to tell you a little bit about that stuff. I want to keep it extremely non-technical. So first I have to tell you, what does fundamental physics mean? It could mean all sorts of things, but often among physicists, it means something rather specific. You could actually have a whole hour-long talk discussing what it means, but I'll try to not do that. So what I mean is a search for a small set of laws which, in principle, determine everything that we can calculate mathematically about the universe. So every single word in there is like short for like a long discussion. For example, the in principle part is very important, because even if you have some laws, some equations that determine what will happen in the situation, it could be, and in fact, it typically is, extremely computationally difficult to derive the consequences of those laws. So for example, even if you could predict the weather using the equations we have for how air flows, we know that small errors build up, and so that in practice, predicting the weather for more than a couple of weeks is impossible, because you'd need to know where every air molecule was exactly right now. Also, there's a lot of stuff that we can't calculate about the universe, apparently. For example, quantum mechanics says that there are measurements you can do where the result is random. We cannot predict what will happen when we measure those things. And so we just give up on that. At best, we predict probabilities of measuring certain things. So there are a lot of limitations to what you could do if you had these laws of the universe that fundamental physics is after, but that's what fundamental physics is about. Now, by 1980, we had one equation that could do a pretty good job of handling the fundamental physics that applies here on Earth. I'm not trying to get you to understand this equation. This equation here is purely to impress you. Really glad to know. But it's meant to, first of all, impress you of the idea, this dream of like a little equation that you could write on a postcard that would be the laws of physics. So you can see that this somehow is supposed to cover quantum mechanics, the structure of space-time, the force of gravity, the other forces of nature, the matter, and the last mysterious link, the Higgs boson, which gives matter its mass. This is sort of bolting together the theory of gravity and the theory of other forces in an ad hoc way, which is definitely not the last word on the subject, but it's pretty darn good in practice. However, already by 1980, some cracks in this edifice were visible, and I'll tell you more about them because that's the exciting stuff. And some of them were fixed since then, but others have widened and gotten more apparent since then. And indeed, theoretical physics has not managed to fill those cracks or to heal the division between gravity and the other forces, despite a huge amount of work among theorists attempting to do that. And so some books have started to come out. These are all pretty written by friends of mine, actually, bemoaning the lack of progress in fundamental physics and suggesting some possible things that physicists should do differently to solve those problems. Now, I'm not going to suggest anything that physicists should do to do things better, because I don't really think I know. But I wanted to point out that this is a brewing debate now as to whether physicists is doing something wrong or whether they're doing the best they can or what. So some have even gone so far as to predict the end of science in big, bold-faced letters. But that's going way too far. For one thing, fundamental physics is just a small part of physics as a whole. Most of what physicists do is use the fundamental laws of physics to actually predict things that are going to happen and to like devise new forms of matter and new kinds of tricks you can do using the laws of physics. So even if fundamental physics is stuck, physics is definitely not stuck. And physics is just a tiny, small part of science. By now, biology is a much more active branch of science than physics, for example. And science itself, I'd say, is really just getting started. There's so many open scientific questions that I believe can be solved and are being solved that it's ridiculous to talk about the end of science now, unless, of course, you think that global warming or artificial intelligence or something will destroy our civilization. So I think the only thing we have to worry about when it comes to the end of science is that, keeping our civilization going. And indeed, the great thing about fundamental physics is that it's the exact opposite of urgent. It will wait. The laws of physics are not like twiddling your thumbs, getting restless. And indeed, if you're an ambitious young person or even an ambitious old person, there are many urgent problems that we really need to solve, much more than figuring out the fundamental laws of physics. This is some little graph of different possible things that could happen with global warming. And you notice that the best outcomes involve going down very low carbon emissions, in fact, getting negative carbon emissions, something that we really don't know how to do at the scale necessary. So there's just tons of things we should be doing that are much more urgent than figuring out the final laws of physics. And I should say, there's also lots of great non-fundamental physics to do. If you just want to do physics, there's no shortage of really cool things to do. For example, we now can make forms of matter, which in that matter seem to have two different dimensions of time instead of the usual one dimension of time. We can make forms of light where light combines with matter and forms a liquid. We can do all sorts of crazy things, and people are doing these, coming up with more and more ideas, none of which involve any new fundamental physics. They all involve exploiting the laws of physics that we already have. So we don't need to worry about taking time to figure out the last steps in the great chain of the laws of physics. But still, fundamental physics is interesting, and that's what I've gathered you here to listen about. So I'm going to talk about that. So what do we know about fundamental physics, and what are the mysteries? Of course, the most fundamental mystery of all is why? That's the question that every child has. And if you've ever had a child, or perhaps been one, you'll know that any answer to such a question begets another such question in an annoying sequence. Now, of course, some people love to tell you that science does not tell you why things happen, just what happens, or maybe how they happen. There's definitely a lot of truth to that. And yet, I think it's really important not to underrate the importance of why questions, because that's often how science moves forward, by asking why. So maybe science never answers why, but they definitely ask why. So let me just give you an example. Why is the sky blue? That's a question that a lot of people have had. So one answer. Well, more than light of other colors, blue light is scattered in all directions by the Earth's atmosphere. So light coming from the sun will hit the Earth's atmosphere, and the bluer light gets scattered more, so the sky that's not right next to the sun looks mainly blue. Good, there's an answer. But why is blue light scattered more? Well, because blue light has a shorter wavelength than most other visible light. Well, that begs other questions. So lots of other questions. One, why does blue light have a shorter wavelength? Well, the answer to this is not so satisfying. No reason. We just call visible light that has short wavelengths blue, or if it's even shorter wavelength, violet. But why does light with short wavelengths look blue? Well, this physicist will say that's not a physics question. Go ask someone else, like maybe a philosopher or a psychologist or a neurophysiologist. You know, the question of whether all of us looking at this see the same blue is a very difficult question, and physicists have wisely managed to get out of the business of answering those kind of questions. Okay. So why does light with short wavelengths scatter more? Well, the answer is it's a general fact. It's a very general fact that almost any sort of wave scatters off small particles with an intensity that's bigger when the wavelength is shorter. In fact, there's a formula for it. The intensity of scattering is proportional to 1 over the wavelength to the 4th power. So when you have very short wavelengths of light, they scatter more. Well, this, of course, would instantly make any child ask another question. So like, why 1 over the wavelength to the 4th power? Where did that come from? And now physicists are very happy to answer questions like that. So that's a good question, they would say. I'm not going to give you the calculation here, but a physicist named Lord Rayleigh showed this in 1871. And it relies, interestingly, on the fact that space has 3 dimensions. There are 3 directions here. And the fact that the number, when you do the calculation, the number 4 here is coming because it's 3 plus 1. You have to do a kind of calculation to see that. It's not at all obvious, but it's really fun. And it turns out if space were 2-dimensional, if we were like flatlanders living on a 2-dimensional universe, then the intensity would go like 1 over wavelength cubed. So there's something really interesting there. That could be a whole lecture on its own. But then the child asks, well, why is space 3-dimensional? Oh, wow. So now that's a good physics question, but nobody knows is the short answer. No one knows. That's just way too hard for us right now. So in fact, there are lots of really good sounding questions of physics that are just too hard for us right now. And basically part of learning physics, especially if you're going into fundamental physics, is like learning everything that people know about these questions, which is not nothing, but it's sort of not an answer. So why is space 3-dimensional? Nobody knows. Why is time 1-dimensional? You may never have even thought of 2-dimensional time, but as I said, we can make materials now in which time acts 2-dimensional. We don't know why time is 1-dimensional. There are broader questions like, are there any truly fundamental laws? I mean, here you are talking about these fundamental laws, but how do you even know that there are any? Or could it be that there's just a succession of ever better and better approximate laws? So like, it could be like in 5 billion years from now, we're still studying physics and we're saying like, we've got much better laws than we did like 2 billion years ago, but we still don't quite know what's going on. We don't know. We have no idea if that's going to be how it plays out, assuming, of course, that civilization survives so that we even have the luxury of worrying about such things. And then, of course, the question, if fundamental laws exist, what are they? Well, we just don't know. We don't know. That's what physicists would love to know. But it's important to realize also that some questions that look like they're way too hard to answer actually were answered. So sometimes you can be positively surprised in this business. For example, why is time so different from space? That sounds just as imponderable and difficult as the ones on the last slide, but it turns out that there's an answer. It's because there's a formula for the distance between 2 points in space-time. So space-time is 4-dimensional, and it has 3 dimensions of space, which we usually call x, y, and z, and 1 coordinate of time called t. And there's a formula for the distance between 2 points in space-time that depends on the change in the x-coordinate, the y-coordinate, the z-coordinate, and the t-coordinate. And you'll notice that the space guys have plus signs in front of them, but the time shows up with a minus sign. If you've ever studied the Pythagorean formula, you'll know that like the hypotenuse is the sum of the squares of these 2 sides. This is sort of like that, but you've got like 3 sides that are like the space and 1 that's time, and the time one is different. So it turns out amazingly that little minus sign there explains practically all the difference between space and time. That just one little thing is enough to cause the difference. And this is basically the idea behind Einstein's theory of special relativity. He realized that all sorts of wonderful things follow from positing this formula. So we now feel like we do know a lot more about why time is different than space.